some of you will be hearing this for the second time, since, as many of you know, we had a practice conference the other day on Friday, where I went over a little bit of this. But since I have more of you here, I just wanted to go over some of the changes that are going to be in the course. So let's see. First of all, we've decided that we were going to have 2 more midterms and a final. Instead, we're going to have 1 more midterm and a final. What we're going to do is, originally each midterm was worth 14% of your grade. So we had this extra 14% we had to redistribute to other parts of the course. Normally we wouldn't do that, but obviously this is very strange in emergency circumstances. So we're taking that 14% and we're just going to divide it between midterm 2 and the final. So midterm 2 will now go up from being worth 14% to 21%, and the final will go up from being worth 32% to 39%. Nothing is going to change about the weight of the test you already took. We're not going to do that. As to when the midterm is, the one remaining midterm, that's going to be it's going to be the week of April 20th. It turns out that for a big course like this that's multi-section, we actually, under the circumstances, we need to get approval from the university as to the exact day, because a lot of people take physics, they take chemistry, they take math, they don't want it to conflict. So we need to get approval for our plan, but we expect it's going to be during the week of April 20th. The final exam will, of course, be at the same time. That I don't believe the university is changing the final exam schedule. That was always scheduled for May 7th. The way this is going to work is, because we have people in all sorts of different time zones now, the idea is that you would get a window that will probably be a 24-hour window during which you'd have to start the test. And once you start it, it would give you some amount of time. So let's say we give you a 70-minute test. We give you then 90 minutes to account for some time for you to photograph it and upload it, which you would do more or less the way that you upload your workshops to Canvas. It's really the same system. A lot of people, I wouldn't say a lot of people, but some people have asked, what happens if, if the internet goes down, or something happens, something happens to your computer and you're left without being able to turn in a test. We're going to be very understanding of that, and we will deal with it, and we'll have procedures, in place for what happens if something strange like that happens. Obviously it's upsetting. You've just done a test and your internet connection dies or your power goes out or something like that. But don't worry, we're going to be quite fair about that. But we'll just come up with some procedure for what happens, and I don't want anyone to worry they're going to fail the test because of something like that. Question someone's asking now is, would it be all on paper or just the open-ended questions? I actually think of those as the same type of questions. I think that what we're talking about, again, we have to get final word on this, but I think what we're talking about is going to be something with open-ended questions. It's a similar format to what you saw. The only difference is that instead of using like a Scantron type sheet to fill out the multiple choice questions, the Canvas can administer that. In fact, some of you have done that already with the quizzes I was doing, the online quizzes I was doing earlier in the semester. So we're working out the exact technological details of how we administer that, but we will figure that out. Let's see. Question: are we allowed to attend other lectures or recitations? It seems that you're supposed to really attend the one that you're assigned to. As far as recitations go, we're trying to sort of keep everybody on the same schedule that they were on when we were all on campus. The idea is not to suddenly let people, change their schedule. It's sort of more that we're being flexible if people are in different time zones, or if for some reason you really need to. We did have somebody who really needed to, to attend a different recitation one time, and it's, that's okay. As far as lectures go, the problem with that is that your permission to attend this Big Blue Button conference comes through our Canvas site. It's not, you don't really have permissions on anyone else's Canvas site to join their conference. So if you meant, like, let's say, attend my other lecture or lecture of, a different professor, if you actually preferred that, but I hope not, that's, I don't really see how that would work. Let's see. I will pay attention to the questions and I'll get to them, but I'm just going to keep talking for now. So let's see. Next thing is I will be continuing to hold office hours. In fact, I'm going to announce some more office hours. Obviously, they will not be on campus. I'm going to send out a link to web. I have a WebEx. I'm not sure what it's called. It's a page. Ongoing conference. There's a link you can use, and that's there's a link you can use for WebEx, and that's how you'll do office hours. So let's see. The question is, can you join a different recitation? I'm going to say this is like on an as-needed basis where you get approval for it. It's not a free-for-all just to change your classes just because of what happens. I know the world feels a bit like a free-for-all right now, but we're going to try to keep this because it's not really fair if we empty out one class and everybody decides they want to be in a different class. Will we be using a proctor service when taking our exams? That is proctor service when taking our exams. That will be up to the university. I have not heard that we're going to be doing that, but that's sort of up to them. So we'll let you know about that. I'm aware some other departments are doing that, and I assume they must have some exceptions in place for people who don't have the requisite internet access. So recitation quizzes on sapling. Somebody's asking about that. Are the recitation quizzes on sapling? The answer is yes, they are. You don't have one this time just because I haven't had a chance to set up the details of that yet. What we'll do is for this week, again, that's going to be one of these things where you have a 24-hour window to start a quiz, and then you get 10, 20 minutes, whatever it is we decide. So normally we would set that so it's the same day as your recitation. Because I didn't have a chance to set that up in time, it's going to be a different day this week, and then we'll go back to that for next Monday. Do you need one? So do you need a webcam or a microphone for recitations is the question. The answer is it certainly would be helpful because, but it's absolutely not required. The university is committed to the idea that not everybody has this equipment, not everybody has the internet access that they need they would need in order to participate at that level, and we're committed to providing the best experience we can for people who can only participate by phone, or even for people who have to participate at different times than we're offering it. But you'll certainly get the most out of it if you have that equipment, which is usually built into a laptop. Is the grading structure still the same? Is it the ranking style for letter grades? If by ranking what you mean is that, is that this was some sort of competition, I want to be absolutely clear that the math department denies that was ever the system. Our position was always that we will index the final grades to how well a particular class does on the final exam. But our position has always been that if everybody does A-level work, we will give an A to everybody. If nobody does even passing work, we will give an F to everybody. And that has not changed. We have very clear ideas about what we expect people to do. We absolutely do not have quotas on how many grades we can give out. So if that's sorry if that's not what you meant, but if that's what ranking means, that was never the system. So it will be the case that it will still be as described on the website. How do we get access to the quizzes? The quizzes will be through Sapling. You'll go to Sapling, and there will be a section on Sapling where there are quizzes, and it'll just be listed as one of the assignments that you can start. Sorry, I'm just waiting for questions, and then I'll move on. Okay. Okay, good. Looks like people have had some chance to ask questions. So, all right. So, what I wanted to do is, because this is kind of an unusual format for all of us. What I was trying to think of is how I would make this seem a little bit more human. My first thought was, I could get some sort of laugh track, and it would be very much like in class. I say silly things and you guys laugh at them. But that struck me as a little artificial and possibly not even the right tone. So what I did actually is one of the things that I've been doing over the last week, in addition to getting ready for this online format, is I've been walking a lot in the park, because it's one of the few things that you're allowed to do these days. So fortunately, there happen to be a lot of parks near my house, many of which have some interesting intellectual activities in them, I guess you might call them. One of them, which I'll share with you in a couple of days, is actually a living monument and museum to the early days of telecommunication. It turns out that about a mile from my house is where the extremely high-powered shortwave radios that beamed signals wirelessly to Europe about 100 years ago existed, and they've made a museum of this particular technology, and I'll share some of that with you within a couple of days. It's really quite interesting. But the one I'm thinking of today is, if any of you live in the Princeton area, you might know of Greenway Meadows Park, where there is the Scott and Helen McVeigh Poetry Trail. This is where you walk roughly a 2-mile course, and every 100 feet or so you can stop. There's a little plaque, and you read a poem. And many of them are they're just sort of simple odes to nature about butterflies and things like that. But so a surprising number of them, I've noticed, are really about time and perspective, which I thought was a particularly appropriate sort of message now. So I thought that maybe on some of the occasions, either I'll start with my description of the telephone technology from the pole farm. That's what they call it, where all the telephone poles were. Or today we'll start with one of the poems, and maybe on some days I'll share other ones. Poetry is not really my thing, but I've always enjoyed this trail. So let me get started with that. Second. My other computer's asking me to do something. I'm still trying to find the best place. See, now I'm looking at the other one. I'm still trying to find the best place to put the other computer with the camera, but I'm going to turn that off in a few minutes because we don't really need it. So anyway, let's see. We will. Oops. Take presenter. There we go. I'm sorry, I'm just working through a small detail here. Yeah. That's not it. That is not even remotely a poem. This is a poem. There we go. So we have here. So this is a poem I photographed last week at Greenway Meadows Park. It is Owl Dream. I'm not particularly good at this, but we'll give it a shot. In my dream, an owl beats spread wings against my window, promising a share of her kill. Small bones lodge in my throat. Blood and sinews stain my tongue. Her wings move faster now, a white blizzard against the glass. Her eyes glare over a harsh beak. She wants my fingers, little animals that squirm on their own in the dark of my sleep. She wants to tell me it's all right, that we can both have everything we need from the same field. There we go. So that's very nice of you, Bilal. Thank you. So, okay. All right. So we go on. What I want to do is I want to start with section 4.2. I realized someone brought to my attention that I had assigned section 4.3 in sapling. I'm going to fix that. As I've mentioned several times, this semester, a certain reordering of the textbook was someone sort of dreamed this up. As I was preparing the lecture notes on 4.3 with the intent to go back to 4.2 as written in the syllabus, I realized that it actually made no sense to teach the topic in that order. So I'm very likely at this point, especially with all this complication of teaching online, I think I'm going to go back to the textbook order. So it's not much different at this point in the course, but I'm going to go to section 4.2 now. So we start with the topic of extreme values. Now I'm going to cut the camera. Everyone who wants to just get one last look at the guest bedroom in our house, and maybe at some point someone requested a house tour at some point during the semester, so we'll try that a little bit later in the semester. For now, I'm going to cut the camera out. There we go. All right. Here we go. So okay, so we're on to the topic of extreme values. This actually it's the lead in to one of the most important features of calculus. One of the most important things that you would do with it if you're interested in using it for applications. I know most of you are in the engineering school, so this is actually where we start to get to we start to build the groundwork for an application called optimization. So a lot of what we're going to do, as you know, I do a lot of examples in class. A lot of what we're going to do is go through definitions. There is a certain there's an intricate but it's a very tight and satisfying framework to how this works, but you need to know a lot of definitions in order to understand it. So first one is let's try and get rid of the glare. Okay, so the first one is we need to know what absolute minimum and absolute maximum are. If we say that f is a function defined on some interval ab, then if a is a number in the interval, in other words, it's its particular value along the x-axis, if f of a is greater than or equal to f of x for all other x in the interval, we say that x is the absolute maximum of f on the interval. If f of a is less than f of x, then for all other x in the interval, then we say f of a is the absolute minimum. That's a real mouthful. Let me try to draw this and see if it makes a little bit more sense. So we have here's a function of some sort. So if this is a and this is b, so we're going to say that I is just equal to the interval ab, then here we have, try to use more colors and make the drawing's a little bit more vibrant than I usually do. So this is f of a, which is of course a y value. And here we have the minimum. This is the lowest point that f achieves in the interval. So this is f of b. So those are the maximum and minimum values of f on the interval AB. Notice that these are values of y that we're talking about. We have a different way of talking about the points at which these occur themselves. In this case, it looks like the minimum value occurs at some point C in the middle of the interval, while the maximum value on the interval occurs at the left endpoint A. As we'll see, sometimes min and max values occur at the endpoint. Sometimes they occur in the interior of the interval. We'll get to when that is, but the point is, just to get the definition down, is that when we talk about maximum and minimum values on an interval, we're talking about the highest y value that the function achieves on a particular interval, or the lowest and the lowest y value that it achieves. When we I'll get to in a minute why we have this term absolute here. It would sort of seem that something either is the minimum or it's not. So what are we talking about with absolute? I'll get to that, but for now, let me just make the screen a little bigger. I'll get to that, but for now, we're just accept that as part of the terminology. Just give you a little bit more terminology here. So we say that f of a is an extreme value, or in Latin, which is often a term you'll hear in math, is an extremum if it is either if it's either a maximum or a minimum. When we talk about the plural of extremum, we use the term extrema. And so if, for example, capital M and lowercase m are the max and min values, then we say that m and m are the extrema of f on the interval I. If we're talking about more than one minimum or more than one maximum, we use the term minima and maxima. So you just want to keep those straight. Certainly nobody's going to fault you if on a test you say minimums or extremums, but it certainly makes you look a little bit better. It's, like I always say, it's like, if you watch the Olympics, which we may or may not be having this summer, if a gymnast does a beautiful vault and then, falls down at the end, the vault was great, but they didn't stick the landing. So you really want to stick the landing by using the terms correctly. So, all right. So anyone have any questions about just about this definition? Yes. Oh, sorry. There's a written sort of typo here. This is f of c. Thank you. Good. One of those errors that we put in to make sure you're listening. Oh, by the way, if you want, I'll just point this out. There should be on your screen somewhere, there should be one of those symbols. Let me see if I can point to it. There should be one of those symbols that means that you can expand to the full screen if you want to be able to see more. It's one of those things with arrows pointing out in all directions. I don't seem to be able to point to it on your screen, but you may be able to see better if you do that. All right, let's go on to the next. Okay. So we next get to the next definition, which is local max, or local max and local min. Local maximum, local minimum, or sometimes in some textbooks they're called a relative maximum and relative minimum. Our textbook calls it a local maximum and a local minimum. So we say if if we have some value, if we have some, again, some x value, which is c, we have x equals c, we say that f of c is a local maximum if f of c is the maximum value of f in some open interval that contains c. And we have a similar but equivalent definition for local min. Local min, f of c is local min if if f of c is the minimum value of f in some open interval that contains c. So I'll draw the picture in a minute. The picture, I think, will make it more clear. But again, like all these definitions, they're kind of a mouthful. So let's, let me just give you the high level view of what this is. It's, perhaps the f of c is not the largest value around, is not the largest value the function attains anywhere, but it's the largest value around. It's the largest value in its own neighborhood. In fact, neighborhood itself is a mathematical term that describes roughly what we're trying to say when we say an open interval that contains c. So you can think of it sort of like if you're standing on a mountain, you're clearly at the top of the mountain. But that doesn't mean that there isn't some taller mountain 1,000 miles away. It just means that for the in your immediate vicinity, you are on the top of a mountain. You're the tallest thing around. So the picture to keep in your mind really. There's that. Oops. Picture to keep in your mind is really this. So if I have a function that looks, let's say, like this. So here's A and here's B. So clearly this is the absolute max. And this is the absolute min. These are in fact the lowest and highest values that the function achieves on the interval AB. But it's also the case that this is a relative, sorry, we're using the term local max, and this point here is a local min. Okay, so Andrew is asking a question. Can a point be an absolute max if it is a vertical asymptote going toward infinity? That's a very good question, but actually no. The notion of any max and min value is that it has to be a function, it has to be a value that the function actually attains. Function cannot be equal to infinity any place, because when we have a vertical asymptote, there are really two things that are going on. One, infinity is not a number, so the function can never be equal to infinity. And two, except in the case of these sort of bizarre situations where the function is defined, it is defined at a finite value coming from the left, but then it has an infinite discontinuity. Usually when we have an asymptote, the function's not even defined at the vertical asymptote. So it never actually attains that value. So I'm going to get to this point because it comes into starker relief with horizontal asymptotes. Some people think that maybe the horizontal asymptote itself is a max or min. That's usually not true. There's a different term for that, and I'll get to that a little bit later. But yeah, that's a very good question. So you can sort of see from this diagram, what the rough idea of this concept is that the local max is certainly not the highest value the function attains, but it is the highest value around. So let's get back to the concept of an open interval. If this is, let's say, C, it's clear that if I were to draw this open interval around the point C, that the local max is the highest value in that interval. And C. I'm sorry, Andrew, did you not hear the answer? Or Oh, okay. I think there were. I just wanted. It looks to me like everybody can hear me. Sorry, can somebody just respond if they can hear me? Because I just want to. Okay, yeah, I'm getting responses. Thank you. Okay, it looked like some people are having trouble. Okay. Okay, so good. So this is what we mean when we say that there is some open interval in which the local max is the highest, is the largest value. If I were to draw the interval, let's say way out here, clearly then the local max that it's indicated would not be the highest value because the absolute max is higher. But as long as there's some open interval that I can draw, which I have, that's what makes this a local max. You might wonder, what do we really care? I mean, don't we really care about the largest and smallest value overall? Why do we care about the local? Why do we care about what's the largest and smallest, the largest or smallest value? Just in some arbitrarily small interval around a particular point. I'll get to that in a minute. It has to do with the application that we're going to be studying, but just bear with me with regard to this definition. Okay, so anyone have any questions about this? About what's on this slide? All right, good. Okay. Okay. So we get to an important result called the extreme value theorem. As you may or may not know, there are a lot of theorems in calculus that end with the phrase value theorem. We've already seen one, the intermediate value theorem, and either by the end of this lecture or sometime early in the next one, we'll get to a different value theorem. But the value theorem we're covering today is called the extreme value theorem. Basically, what it says is if f is continuous on a closed and bounded interval, AB, then f takes on both an absolute minimum value and an absolute maximum value on AB. This is one of these things that seems like, what's the big deal about that statement? It seems almost obvious, but I'm going to show you shortly a couple of counterexamples to show why these conditions are necessary. For one thing, let me just be clear about what closed and bounded means. So closed and bounded as an interval means that we're talking about an interval that includes its endpoints and that only extends a finite amount in one direction. The bounded part is necessary because what many of you may not realize, and I don't necessarily want to get into the reasons for this, is this interval, infinity to infinity, negative infinity to infinity, is actually a closed interval, even though we write it using symbols that most people associate with open. This is kind of an advanced topic, but this is an example of an interval that's closed but not bounded. So that's why I need to say that it's bounded. But what you think of as a closed interval is probably what is really a closed and bounded interval. So that's so anyway, that's what the closed and bounded is. Just draw a couple of examples of this. So if we have, say, A, and that's B. So here we clearly have an absolute max, and here we have an absolute min. So here, of course, we have f is continuous on closed interval AB. So the conditions are met. We actually do, we have a function that's continuous on the closed interval AB. And in fact, you can see that it clearly does achieve both a min and a max on both an absolute min and an absolute max on that interval. the example I've shown shows it achieving the absolute min and the absolute max at points that are in the middle of the interval. You know, we might call this, let's say, C1, and we might call this C2. Here's just another example of that, where we have, let's say, a function that looks like this. So that's B, that's A, and here we have the absolute max, and down here we have the absolute min. And those points are attained at the endpoints of the interval rather than in the middle. Either of those can happen, and not only that, but in some cases the max is in the middle of the interval and the min is on one of the endpoints, or vice versa. So you can have any combination of that. That may seem, again, like one of these things that's not that significant, but I'll get to that in a minute. You'll see why I'm making it an issue of what the endpoints are, you know, what happens in the interior of the interval and what happens on the endpoint. So just keep that issue in mind. So let's see. Actually, I had it in my notes, so I'll just draw it anyway. Here, that's an absolute max, and that's an absolute min. Keep in mind that although you might notice this function going off in that direction, you might say, well, it looks like it has values that are higher. But the point is that this is the absolute max on the interval AB. We don't really care what's happening outside of the interval AB. So that's why I don't care about these points here and the fact that they appear to be higher than the absolute max. If we restrict ourselves only to what's going on in between here, you can see that that is in fact the absolute max, and it occurs at one of the endpoints. All right. So, okay. So the point of this theorem is that it says that if I have these conditions met, that the function is continuous on a closed and bounded interval, then there is an absolute min and an absolute max. I'm going to show you a little bit later some counterexamples of functions that never actually attain a maximum or minimum value. We'll get to that in a minute, or a few minutes rather. So throwing a few more definitions at you. This is the next definition is what's called critical numbers. Our textbook actually calls them critical points. I prefer the term critical number, just to emphasize that we're not really talking about like an XY pair. Certainly, you know, if we have a function, the X value defines a particular Y value, so you can graph a point as an XY pair, but we're specifically talking about the X value. That's why I prefer to call it a critical number. It's not a pair of XY values, it's just a number. So say a number C in the domain of F is called a critical number, or in our textbook's language, a critical point, if either F prime of C is equal to 0 or F prime of C does not exist. So see what does this look like? We have some function that looks like this is y equals f of x, and this is C1, and this is C2. Let's look at what's going on at these points. So at C1, look at the tangent line. The tangent line at that point is horizontal. So what we would say is that f prime of C1 is equal to 0 because the slope of the tangent line is 0. It's a horizontal tangent. Here, as we've seen earlier, when a function comes to a corner like this, what we would say is that f prime of C2 does not exist. In other words, the derivative is just undefined at that point. Certainly the case that f exists at C2, but its derivative is undefined. Just recall, we had done this example that since the derivative itself is a limit, if you were to approach this point from here and ask, what does the slope appear to be at that point? You would conclude, just eyeballing it, that you have a slope of m equals 1 if you approached on the right. If you approach this point on the left, you might conclude that the slope was m equals -1. That's how we, that's sort of an intuitive understanding of why it is we say the derivative doesn't exist, because when we find derivative through its limit definition, we would get two different values on the left and right, which means that the two-sided limit doesn't exist. I'm going to wait for the questions because it looks like there's now starting to be some question activity. Okay, so let's see. Are all critical numbers local max and mins? So you're asking. So you're at. These are two actually very good questions. So are all critical numbers local maxes and mins? The answer is no. There's the converse, however, is true. We'll get to that in a minute. It turns out that all local maxes and mins are critical numbers. It is possible. I'll show you actually right now. I'll show you. I'll show you an example where you have a critical number that's not a local max or min. Next question is, how do you know which point to pick for f of c? I'm going to show you that in a minute. That's when we get to the actual procedure for solving a problem. The short answer is you find the derivative and you look for places where the derivative is either equal to 0 or where the derivative is undefined. So we'll get, once we get out of, once I get past the definitions, I'll do an example where we see all of that. So let me just show you briefly an example of a critical number that is not a max or a min. Suppose that I have like that. So at this point here, we think of the tangent as just kind of grazing the curve, but remember the tangent is really the slope of the function at a particular point. In this case, the tangent actually crosses the curve, but what you can see is that clearly the slope of the curve at that red point is 0. So at this point, we would say f prime of c equals 0, but f of c is not a local max or min. So that's an example of a situation where you have a horizontal tangent, but you don't have a local max or min. That's a topic we're going to investigate in quite a lot of detail a couple of sections from now. But what is true is what is going to be true is that any place where you have a local max or min, you do have a critical number. It's just the converse of that is not necessarily true. Okay. So just wanted to give you another example of a critical number. So let's see. All right. So question is C2 a critical number? of this function. This is the part where I'd be standing in the front of the class and asking for input. So feel free to type something if you want. So we've got some maybes, some yeses, some nos. Okay. First of all, I just want to respond to one of the comments. Someone asks, is it a local max? I want you to separate in your mind the issue of whether something is a critical number from whether it's a local max. The definition of a critical number is precisely what I've written up here. This is completely separate from the question of whether it's whether the point actually turns out to be a local min, a local max, or neither. So the number is critical if it meets either of these definitions. And I would say clearly we have f prime of C2 equals 0. So C2 is a critical number. Okay. So what about C1? Is C1 a critical number? Everybody says no. Actually, C1 is a critical number. Go back to the definition. Definition number 2. F prime of C1 does not exist. Why does it not exist? Well, if function is not continuous at C, it is not differentiable at C. This is just an important point, is that in order for a function to be differentiable, we talked earlier when we covered the definition of the derivative, in order for a function to be differentiable at a point, it has to be continuous at that point. Functions can be continuous without being differentiable. If you look, for example, at C2 here, we have a function that's continuous at C2, but it's not differentiable, but the converse is not true. Continuity is just a minimum condition for a function to be differentiable. If you don't have that, you don't even get to the question of how you would find the derivative or whether the two-sided limits are the same. It's just the function can't be differentiable. It doesn't have a tangent line if there's this huge break in the function. In theory, it might be possible to define some concept of left differentiability and right differentiability, just like we did with continuity, but we don't really do that. It's not as useful a concept. So in any event, but even so, even if we were able to say, let's say that this function is left differentiable at C1, that's not the question. The question, is it differentiable? Which means, is it two-sided differentiable? And it's not. It's not continuous at that point. So just remember that rule. If it's not, function's not continuous, it's not differentiable. So this is kind of a subtle example because I'm trying to make sure you don't have in your mind the idea that all critical numbers look like peaks like this, peaks or valleys. Here's a simple example of where it's not a peak or a valley, and here's a simple example of something that just looks totally different. So, okay. Any other questions about definition of critical numbers? C1 be an absolute max. Are you talking about C1 in the blue diagram? Yes. Well, that sort of depends on what's going on in the rest of the function. I haven't drawn the whole function, so we don't really know. Remember, it's only actually, I shouldn't say that. It is possible to talk about an absolute max for a function, even not on a closed and bounded interval. We don't really know because we don't really know what else is going on in the function. If the function is limited to what you see here, then yes, it is. Okay. So we now get to the topic of location of extrema, and this is one of the central results in calculus that enables us to do the optimization application that I mentioned. This is what's often called Fermat's theorem on the location of local extrema. By the way, the reason I'm pronouncing it that way is because Fermat was French. You often hear some people say this is Fermat, but almost everybody in math department will say Fermat. Fermat was actually a very prolific mathematical hobbyist. He wasn't even a professional mathematician, but he's very well known. I'll tell you in a minute what the story was behind him, but first let's just cover this theorem. Fermat's theorem on location of local extrema says if f of c is a local minimum or local max, then c is a critical number of f. So this is the connection I had alluded to earlier, that one of you alluded to in a question. So what this means really is that local mins and maxes can only occur at critical numbers. Therefore, we can find all the local mins and maxes of f just by looking only at the critical numbers, and that's their significance. So if you look here, we can see is that if I were to draw a function that looks, let's say, like this, what you can see is that here I have a local max, and here there's also another local max, and here we have a local min. And if you look at what's going on here we have, I label these C1, C2, C3. This is f prime of C1 is clearly equal to 0 because we have a horizontal tangent. Here we have f prime of C2 does not exist. And then here, for the reasons I covered in the last slide, we have f prime of C3 does not exist. So these are the only types of places where local mins and maxes can occur. Okay, so I'm getting a question. Why can you have multiple mins and maxes? It's because they're two different functions. The answer is no. This is shown as one function. The reason is because we're talking about local mins and maxes, not absolute mins and maxes. If you think about sort of like my mountain analogy, here we've got, let's say, some terrain where I've got, increasing mountains. This is Everest, this is K2, this will be, trying to think of a mountain in New Jersey. I don't think we have any. So let's call this Mount Pocono. We'll go to Pennsylvania for that. So so here, this is, sort of peak 1, this is peak 2, and this is peak 3. They're all peaks. It's clear that this is the absolute max, but peaks 1 and 2 are still peaks 1 and 2 are still they're still they're still maxima in some sense. And this is what we're talking about with local maxes, is that it's still, if I were to draw some open interval around that location, it's the highest thing in that interval. So okay. Anyway, I hope that answers the question. So, all right. So the point is that these local mins and maxes can only occur at critical numbers. And that's the significance of finding the critical numbers, because they're all the candidate points for where the local mins and maxes are. If we want to find them all, those are the only points we have to look at. So this is going to be the sort of theorem that sums up how we're going to do optimization. Is if f is continuous on the closed interval AB, and f of c is the minimum or maximum value, in other words, the absolute min or max of f on AB, then there are only two possible choices. Either c is a critical number or it's one of the endpoints. So those are the only types of places that absolute mins and maxes can occur. Either at some local min or max, could be also be the absolute min or max, or at the endpoints. This is a remarkable result because if you think about it, the total number of points inside an interval is infinite. But what this is telling us is that we only have to look at a very small number of these points, just the places where there are, where we either find that we have a critical number or at one of the two endpoints of the interval. So it narrows down the problem of finding the highest and lowest value of a function down to, a very small number of points that we have to check. So let me see. Okay, so let me just sort of just wrap up the definitions by asking the question, why does f have to be continuous on a closed interval in order for this rule to apply? So first of all, let's take a look at this function. So here, f is not continuous on AB, right? It's only continuous for certain intervals in AB, but it's not continuous on all of AB. Now notice that f has no min or max on AB. You might think, if you look at it, there we go. You might think about this, is this a max and is this a min? But the fact is they're not, because the function never actually gets to those points. It's, if you can see, it's an open circle, so it never actually gets as low as here. It just keeps getting closer and closer to that. Like if I were to say that this is the value 1, what this function does is it gets to 0.9, 0.99, 0.999, 0.999. Let's put a million nines in there. You can get as close as you want to 1, but you never actually get there. So you can't really say that 1 is the maximum value in this drawing. And it's the fact of the lack of continuity that allows that to happen. Somebody asked, well, my morning class, somebody asked, well, why isn't the maximum just the number that's right before 1? But this is the nature of excluding an endpoint from the interval, is there is no number that's right before 1, because let's suppose that you think that 0.999999999, is that the number that's right before 1? Well, no, because I can always just add another 9 and get a little bit closer. So there is no number that's right before 1. The term we would actually use for this is least upper bound. You may have seen this in pre-calc or algebra 2. The term that we use in upper level math courses for this, we write it in Latin. We write the term supremum. So there is a meaningful sense in which that is the top of the function. It's just not the maximum, because the function never actually gets to that point. So it doesn't have a maximum value. Let me just put in another example of a function that's not a function that breaks the conditions here. So here, what we have is let's call this, let's say y equals 1 over x. This is defined on 0, infinity. So the interval is not closed. So here we have a function that's not closed. And what we can see is that since this is approaching positive infinity, it doesn't have a maximum value on that interval. And again, it's the fact that the interval is not closed that allows that to happen. You might say, what about 0? Isn't 0 the minimum value? But if you look at what's going on, the curve is approaching 0 as a horizontal asymptote, but it never actually gets there. So once again, for the same reason as in the drawing on the left, the 0 is not the minimum value because there's nothing that you could plug in for x in that function that would cause y to be 0. It just never attains the value 0. It's not the minimum value. Final sort of pathological case that you need to see is this, which is what if I have something like this? So here we have f is defined on AB, that is not a closed interval. We sometimes refer to that as a half open interval, but a half open interval is neither open nor closed. Again, that gets into topology. I don't really want to get into why that's true. But so since AB is not closed, but F does have absolute min and max. Here we have absolute max. Here we have the absolute min. So this is, again, one of those sort of slippery concepts about a theorem. I said that if f is closed, if f is continuous on a closed and bounded interval, then it does attain a min or max. That doesn't mean that it can't attain a min or max under some other circumstance. It just means that the theorem doesn't say that it does if you don't have those conditions. So it's possible the function does have an absolute min or max. It's just not guaranteed by the theorem unless the interval is closed and bounded, and unless the interval is both closed and bounded and the function is continuous on that interval. Is a critical number? Well, actually, no, because the function is not even defined at a. And in order for a number to be a critical number of a function, it has to be in the domain of the function, and it's not. You might ask, well, okay, is b a critical number? This, believe it or not, is one of the things that we argue about in the math department. There is one instructor who is very adamant that endpoints are critical numbers, but it's just so, again, he is technically right from a topological standpoint, but the way that our book defines it is that critical numbers are evaluated only in the interior of an interval, so we treat endpoints differently. Strictly speaking, for reasons that are, again, get into topology and I don't want to explain, endpoints are critical numbers, but we're never going to ask you something that asks you to distinguish that. Because this is the way our book does it is it says no, and there's an actual debate about that. So you can basically just ignore the last 20 seconds of what I said, just assume that critical numbers are only relevant, in the interior of a function's domain. So. I'm just waiting for a question. Function was in jumped on discontinuity to the left. Would a be a critical number? Then yes. Yes. because then it would be in the interior. It would be in the interior of the function's domain. It would be discontinuous, so it would be not differentiable at that point. Question was, what if I had something like this going on like that? Yeah, then A would be a critical number. Okay, anyway, I just want to move on because I want to make sure I get as far as I need to today. So let's, all right, so this now, because we're going to put this all together into a procedure to find the extreme values of a function. So since we know that the extreme values, the absolute min and max, can only occur at either critical numbers or endpoints, this is what's called the optimization procedure. This process is called optimization. And what it is it says in order to find the absolute extrema of a function on a closed interval, we find all the critical numbers. We do that by finding the derivative of the function. We set the derivative equal to 0 and solve for x to see where the derivative is 0. We also look for places where the derivative is undefined. Next thing we do is, since we know that the min and max have to occur at one of those points or at an endpoint, we evaluate f at all the critical numbers and at two endpoints, and then we simply pick the highest and lowest values. And like I had said earlier, the reason this is sort of a remarkable process is that since there are actually infinitely many numbers in any interval AB, there are infinitely many numbers here. We're usually talking about looking at only maybe 2, 3, 4, or 5 of them. And it allows us to find, even in cases where we can't graph the function, it allows us to find that. I'm just going to respond to a question. Andrew, you said you thought the function needs to be continuous. The function needs to be continuous in order to guarantee that it has a min and max, and in order for this specific process to work. What I was trying to do in the last slide was show what happens if those conditions don't apply. In other words, why it is that you might not get a min or max if the function is discontinuous. That was what I was trying to show. So assuming the function is continuous, this process applies. And we can still talk about critical numbers of a discontinuous function. We just can't use them in this process if the function is discontinuous. Okay, so what I'm going to do here is I'm going to just show you how to find the extrema of a particular function. So the first thing we need to do is find the critical numbers of this function. So this is a function, it's a cubic function, 2x cubed minus 15x squared plus 24x plus 7. And we want to find its absolute max and min values on this specific closed and bounded interval, 0, 6. So what I'm going to do is find the derivative, f prime of x. Just do that. This is a very simple derivative to find. 6x squared minus 6x squared minus 30x plus 24. So what we want to do is find where that's equal to 0. So I'm just going to factor it and see if we can do it that way. So this is going to be 6x squared minus 5x plus 4. That factors very nicely. This becomes 6x minus 4, x minus 1. So we're just going to solve f prime of x equals 0. And that gives us x equals 1 or x equals 4. Those are the two places where the derivative is 0. So what we would say, oh, and also we'd say that f prime of x is defined everywhere. So there are no points. So there are no points where f prime does not exist. So we don't have to worry about that type of critical number. We only have points where f prime is 0. So we can say critical numbers are 1 and 4. So those are the two critical numbers of f. So for step 2, we're going to do is evaluate f at the critical numbers and endpoints. Oh, so the question is, how do we know there are no points where the derivative doesn't exist? Well, I mean, the derivative would only not exist if we know what the expression for the derivative is because we found it through the power and linearity rules. The only way that a derivative would not exist is if that expression were undefined someplace. But 6x squared minus 3x plus 24 is just a quadratic function, and we know that quadratic functions are defined everywhere. So, we'd only be looking for something like if the derivative had a tangent in it or something like that, then we'd know it would be undefined at vertical asymptotes. So we evaluate f at the critical numbers and the endpoints, and I will tell you that the most common mistake that you ever see when grading these is people evaluate f prime at the critical numbers because they know the critical numbers have something to do with f prime, so then they go and plug the critical numbers back into f prime. But no, what you want to do is you want to plug them back into f because we're looking for the highest and lowest values of f, not of f prime. So what we do is we're going to evaluate f of 1, and I've already done this. F of 1 is 18. F of 4 is -9. And then we want to do the two endpoints of the interval. F of 0 is 7. And f of 6 is 43. So these are the critical numbers, and these are the endpoints. So that's why we're evaluating at those 4 points. And what we can easily see is that -9 is the lowest value that f attains, and 43 is the highest value that f attains. So what we can do is we can conclude that the absolute min is -9, and the absolute max is 43. And that's the answer because we were asked to find the absolute min and the absolute max. And so that's the answer. I should point out that a lot of people are going to say, isn't 4 the absolute min and isn't 6 the absolute max? Those are the places where the absolute min and max occur, but they are not the absolute min and max themselves. Those are slightly different questions. Absolute min is going to be a y value. And okay. Right. And f of 1 is a local max, but f0 is just a critical point. We actually don't have at this point, I mean, I haven't looked at the graph of the function, but we don't at this point have the analytical tools to say what the other critical numbers are. There is a way to do that, and we'll get to that in a couple of sections. Again, as you might guess, the answer is going to involve derivatives, but just sort of hold up on that. Okay. Anyway, what I want to do, I can stick around for a little bit after class, but I just want to finish the last topic here that appears in the section. The last thing that appears in section 4.2 is something called Rolle's theorem. It's also called Rolle's lemma. A lemma is sort of like a little theorem that you use to prove another theorem, but Rolle's theorem really deserves to be a theorem in its own right. So what Rolle's theorem says, let's get a picture of it up, is, so if we assume that f is continuous on a closed interval AB, and that it's differentiable on the open interval AB, and we're going to assume that FA is equal to FB, then what it says is that there must be one number C in the interval where the function has a horizontal tangent. In other words, where f prime is 0. So let's draw this. So clearly what we have here is this is fa equals fb. So what it's saying is that if I have these circumstances, as long as the function remains differentiable, in other words, as long as we don't have some situation like this, where that's AB, here clearly the slope is 1 and the slope is -1, and it never actually achieves 0. As long as the function remains nice and smooth and differentiable, there has to be at least one point where the derivative is 0, in other words, where the tangent is horizontal. And as you can see, in this case, there are actually 2 points, but what Rolle's theorem does is it guarantees that there's at least one such point. So this is sort of an important result, and we'll get into this more. There's a generalization of this, which has another value theorem type of name, but we're going to use that. This is sort of a thing they stuck into this chapter because you kind of need it in order to go on to the next, into this section, because you need it to go on to the next section. Let me just show you what you would be asked to do with Rolle's theorem before we break. Verify that Rolle's theorem is satisfied for f of x equals sine x on the interval pi over 4 to 3 pi over 4. What we know is that the sine function looks like this. And this is roughly pi over 4. And this is 3 pi over 4. So what we can see is that the sine of pi over 4 is equal to root 2 over 2. We know that. And the sine of 3 pi over 4 is equal to root 2 over 2. So if we say that a equals pi over 4 and b equals 3 pi over 4, then it's clearly the case that fa equals fb. So we have that part of Rolle's theorem is satisfied. A, that's b. We have fa equals fb. And then what that does is, if you notice, it guarantees that there is, in fact, a point in here. We know that there is a point where there's a horizontal tangent. We could easily find it because if f of x equals sine x and f prime of x equals cosine of x, we say where is cosine x equal to 0 in the interval ab. It's equal to 0 at a lot of places, but most importantly, it's at pi over 2. So the critical number c is pi over 2. Okay. Anyway, sorry, I'm a minute over time, and I know some of you have recitation, so I will let you go. Make that big trek across Voorhees Mall to back to Murray Hall for a recitation. Anyone who wants to stick around who doesn't have recitation, I can answer the questions that you had. I'll stick around for another 5 minutes or so. Anyway, thank you for coming. I hope this was just like being in class, right? So I will see you all on Wednesday evening. And have a good night, everyone.